Today we shall discuss about the elemental semiconductors. You know that the electronic materials are mostly semiconductors, and it can be categorized into a large number of materials. Practically it is a material family, and broadly we can divide semiconductors into two groups. One is the elemental semiconductor, another is the compound semiconductor. So, one is elemental, another is compound. As the name implies that this elemental semiconductors, this is a particular element or a material, and it is not a compound at all. So, if I would like to name some of the elemental semiconductors, obviously silicon, germanium, diamond, you know that diamond comes from carbon basically, then gray tin which is known as alpha Sn. So, these are the materials which are the elemental semiconductors. Now, among these semiconductor materials which are elemental in nature, silicon is the most important electronic material because of its application in the integrated circuit. Now, what are the advantages of silicon? Let us first see. The advantages of silicon are, there are many advantages. One of the advantages is the relative ease of passivating the surface by oxidizing it in a controlled manner, right. Now, what is the implication of this statement? Relative ease of passivating, you see that I have mentioned here the relative ease of passivating. First term which is coming is the passivation. What is passivation? Can you tell me what is known by the term passivation? And there is a clue that passivation of the surface. So, what is passivation? Making the surface unreactive, exactly. And if you tell me that why this is required, because you see that in silicon or in any material, basically it is covalent bonding are there, and if you cut a piece from it, say this is a silicon crystal and you are taking a cut of it. So, what will happen? Basically you are cutting the bonds, you are cutting the bonds, you do not know actually, somewhere there will be bond. So, at the top of the surface there will be unsaturated bonds which are known as the dangling bonds, and these dangling bonds are very reactive. So, that is why if you keep a piece of particularly silicon or that type of material, within a few seconds a thin oxide layer will grow at the surface. It is because of it will take the aerial oxygen, and if it takes the aerial oxygen from the atmosphere, then with the unsaturated bonds there will be an oxide layer of SiO2, very thin layer of SiO2 SiO2, right. Now, for silicon this is very advantage, this is an advantage. Why? Because SiO2 can be made very easily. This is basically known as the oxidation. So, when you will come to learn about the different steps of IC fabrication in your semiconductor technology class, you will find that oxidation is an important step for fabrication of integrated circuit, like your ion implantation, diffusion, annealing, lithography. So, oxidation is very important term or the process basically. This oxidation in silicon, it can be done very easily, unlike in germanium. You cannot grow germanium oxide very easily on the germanium substrate or germanium wafer. Why? Because it is unstable in nature, you do not have any control on it. If you take another example for say gallium arsenide, indium phosphide, there are several types of semiconductor, cadmium telluride, zinc oxide. Oxidation layer in a controlled manner growth of oxidation layer in a controlled manner is very difficult except in silicon. So, that is an advantage that you can grow SiO2 in a very controlled manner, because that is you know that this silicon is basically the host matrix. Silicon is the host matrix here, and always there will be dangling bonds. So, by passivation, what is the advantage of passivation? Why we need passivation? Why we need passivation? No, one is reactivity will be reduced, that he told earlier. Then what is our application point of view? So, for our application point of view, what is the advantage? No, not only dust or impurity, the advantage is that yes, during diffusion or ion implantation or lithography, you know that masking is done. Masking is done, and here SiO2 and acts as a mask for those processing. So, that is very important thing. And in some devices like say MOSFET, you need an oxide layer, MOS, metal oxide semiconductor. So, for silicon, it is a God gifted item that silicon oxide can be grown very easily and without any difficulty, and it is very stable. So, that is why MOS can be fabricated very easily using silicon. Such thing is not there for compound semiconductor like gallium arsenide, indium phosphide. It is not very easy to deposit gallium oxide. There is no such mature technology these days. So, that is one important thing, that you can oxidize the surface to passivate the dangling bonds. And this stable native oxide thus formed, you see that I have mentioned that this stable native oxide layer thus formed reduces the surface recombination velocity. That is another advantage for the oxide layer. Now, what is surface recombination velocity? What do we mean by surface recombination velocity? Can you tell what is surface recombination velocity? Suppose you are making one photo detector. You are making one photo detector which detects light. So, for photo detector, generally light falls on a substance, on a surface. So, if this is a silicon material and light falls on its surface, it is incident on its surface, then what will happen? The light will be absorbed by the surface only, because of the oxide layer etc. It will be absorbed by the surface. Another point is that as soon as it will be absorbed in the surface, electrons and holes will be generated, and those electrons and holes will recombine in the surface itself without going inside the bulk of the material. So, that means the output from the detector will be very, very less, because that will be a surface phenomena. That will be a surface phenomena, but we want to exploit the whole of the bulk. If I use a 300 micron semiconductor and the surface is say 1 micron, 2 micron or 10 micron, then what about the rest 250 to 300 micron? So, we cannot exploit the electrons and holes in the bulk of the material. Okay. So, if you passivate the surface, then the surface recombination velocity becomes less. That means, the recombination will not be held in the surface itself, it will be held in the bulk of the material. Obviously, the recombination of the electrons and holes. Another important advantage of silicon is that its hardness allows large surface wafers to be handled safely. You know that this processing technology of silicon, it is basically the processing technology of silicon, it is basically 6 inch, 8 inch or even 12 inch wafer is handled. That means, the whole wafer is placed inside the furnace or inside the ion implanter or inside the diffusion chamber for processing. Basically, it is a planar technology. Planar technology means, say this is your substrate or the wafer, the whole wafer is processed. First there is an oxide layer all through the surface of the wafer, then there will be photolithography, then there will be etching, then there will be diffusion or ion implantation, then there will be metallization. So, this whole planar technology we use generally the large wafer, that means 8 inch, 12 inch, 14 inch wafers are used. Okay. So, for those processing basically you need some hard material, otherwise what will be happen, if it is brittle then during processing it will be broken. So, that is the reason that its hardness compared to indium phosphide or gallium arsenide, the compound semiconductor, the silicon is more hard compared to the other compound semiconductors or the elemental semiconductors. Another thing is its thermal stability allows high temperature processing related to diffusion, oxidation, annealing, etc. High thermal stability is very high, that means processing temperature can be very high, because we discussed in our diffusion and implantation that particularly for diffusion 1000 degree, 1200 degree centigrade temperature is required. For oxidation also high temperature is required. After ion implantation what we do? We subjected the material into annealing, right. Can you remember that annealing is done, rapid thermal annealing or conventional type of annealing is done. So, all those steps, all those processing basically related to high temperature. So, that means it must withstand very high temperature, otherwise there will be thermal degradation of the material. So, that is another advantage, that high thermal stability it allows, and low cost, because you know that the silicon is basically freely available in nature, it is abundance. So, it is the costing is very low compared to other material, because other material cannot be naturally obtained, say germanium or gallium arsenide or indium phosphide or nitride semiconductors, naturally it is not generated. You have to use some chemical means or some processing technology, special techniques for the growth of those materials, but silicon is abundance in nature, and during our crystal growth I shall show you that how silicon is taken from the normal sand, it is processed, purification etc., and then bulk silicon crystal is grown, and a piece of those silicon crystal which is known as the wafer or the substrate is used for IC technology. So, that is abundance in nature, that is why it is low cost. So, this is these are the advantages of silicon. The most important advantage is that the oxidation, okay, which is not available for other materials. Then what are the limitations of silicon? Is there any limitation for silicon? Yes, there is limitation for silicon. One limitation is the magnitude and type of its energy band. The magnitude is 1.12 electron volt. So, this 1.12 electron volt is an energy which is associated with the emission at the 1.1 micron. What is the relation between the band gap and the emission wavelength of a semiconductor? Yes, lambda equals to 1.24 by Eg. So, if you use this 1.12, so you will get just only one wavelength. It is not suitable for visible, obviously, because the band gap is 1.12 eV. So, it is infrared, not visible region, and it is indirect type. We know, we have discussed that indirect type limitations is that it cannot be used for optoelectronic sources because of the conservation of momentum. So, that is why it limits the optoelectronic application. So, that is the silicon is not used for particularly optoelectronic sources. You cannot make LED or laser from silicon. Another important limitation for silicon is that it has lower carrier mobility. Lower carrier mobility. What is mobility? Drift velocity per unit electric field. So, this carrier mobility, that means mobility of electrons or holes, because when we talk about mobility in a semiconducting material, there are two mobilities. One is the electron mobility, another is the hole mobility. And why the mobilities differ? Why there is a different types of mobilities? Yes, because of the difference in effective mass you will get different values of the mobility. So, now carrier mobility. Say for silicon the mobility is 1600, obviously it is centimeter square per volt second in CGS unit. I am writing the electron mobility, not the hole mobility, right. Then for silicon it is 1600 centimeter square per volt second. Then germanium it is 3900, but if you compare with gallium arsenide it is 9200, or say indium arsenide it is 40,000, or indium antimonide it is 77,000, very high mobility. Okay. So, these are the mobilities of different kinds of semiconductors, and if you compare this mobility you will see that for silicon the mobility is very less, it is 1600 only. Okay. So, this is another limitation, because if the mobility is very less, so that means you cannot use those material for high frequency devices, because only integrated circuit is not the end. You have different types of devices. One is say laser, LED, detector, then microwave sources, impact diode, read diode, pin diode, etc. There are different types of devices, and microwave device is very important for particularly this communication type of thing, for modulation of signals, etc. So, silicon is not used because of its band of its mobility, the mobility is very less compared to say gallium arsenide or other materials, say indium antimonide 77,000 is very high, and this mobility is high because of the electron effective mass. You see that for silicon the electron effective mass is 0.19, and for germanium it is 0.082, for gallium arsenide it is 0.067, for indium arsenide it is 0.023, and it is 0.014. These are the effective mass, 0.19 m0, 0.082 m0, 0.067 m0, 0.023 m0, and 0.014 m0. What is m0? m0 is the rest mass which is given by 9.1 to 10 to the power minus 31 kg. Okay. So, you see that basically as the effective mass decreases, the mobility increases. So, this mobility is an important parameter for selecting a material for a particular application, and for silicon we find that it is not suitable for many applications. So, what are the emerging materials based on silicon? Because silicon is very cheap, it has many advantages, it is readily available in the nature, and obviously it is the technology is very mature because of the IC processing technology. So, can we use silicon for those applications where the elemental silicon cannot be used? Yes, there are many types of methodologies using which you can use silicon in different kinds of applications. One is based on the silicon nanostructures, and you have heard the name of nanostructures. And what is nanostructure? Within 100 nanometer. No, that is not the definition. No. What is basically nanostructures? Exactly, because of the structure some of the properties are changed, and those are available when you reduce the dimension of the material to what is said in the nanometer region, say 10 to the power minus 9. So, what are the implications of nanostructures? Implication of nanostructure is that during a fabrication of nano, the motion of the carriers is quantized. Now, what is the meaning of the motion of the carriers is quantized? Say you are in this room, okay. Now, in this room you can move in all the three directions x, y, z. Now, suppose if the height of the roof is reduced, okay, if the height of the roof is reduced to say 4 feet from the floor, can you move in the z direction? You cannot move in the z direction. You have, your only option is to use the x y plane. That means, you can move along the x y plane, but you cannot move along the z direction. So, that means, your movement is confined in the x y plane. So, two dimensional effect will be there. Okay. So, though you are 3 dimensional material, you are a 3 dimensional species, even then you cannot use the z direction because of the reduction in the dimension. Similarly, suppose you are standing in this room and these two walls are made closer to each other, then what will happen? You can move along the z direction, but you will not be able to move along this x y direction. So, that means, your movement is quantized. Now, only in one direction your motion is allowed, right. So, these are the examples of the confinement, and when we tell that it is a carrier confinement effect, carrier confinement means the confinement of the electrons and the holes in our case. If you use a metallic film, then it is the electron only, because you know that the concept of hole is not there in metal or in other materials except in case of semiconductors. So, when we talk about the confinement of something, that means it is the confinement of the electrons and holes. Confinement of what? Their motion, their movement. You are restricting their movement. So, under such a circumstance, because of the quantum mechanical phenomena, many new thing happens. The density of states is changed. Density of state, what is density of state? Density of state is known as the yes, actually per unit volume, the number of available states for a particular carrier. Number of available states. Available states means, let us take the same example, that suppose there is a material and at normal temperature the holes are, the electrons are there in the valence band. So, if you excite the electrons, then what will happen? They will move to the electrons are there in the valence band, and if you excite the electrons, so they will move to the conduction band. That will depend on the density of states in the conduction band, number of available states in the conduction band, that is the density of states per unit volume, that is why it is known as density. Okay. So, it will depend on the density of states. So, now during quantum mechanical treatment, or if your movement is restricted, if your movement is confined, then this density of states for bulk material, it is what is the nature of the bulk material density of states? It is parabolic in nature, E equals to h bar square k square by twice m star, p square by 2 m, E equals to p square by 2 m. So, E equals to p square by 2 m, and what is p? H bar k. So, h bar square k square by twice m star in our case, because we have discussed about the effective mass, because of the curvature in the bands, we do not use the normal rest mass in our case, we use the effective mass, right. So, this is parabolic in nature, this density of states is parabolic in nature, but if the confinement is there and the motion is reduced, it is confined, then this density of states will be different from the bulk density of states. Okay. It may be staircase function and other functions are there. I am not going into details of those things, these are mathematical. So, you can calculate those things by solving the Schrodinger wave equation, but in our case we will not go into those things, only we can assume that because of the restriction or the confinement of the movement of the carriers, new phenomena is observed, and that is the implication of the nanostructures. Okay. And many properties, I shall show you some of the properties in our lecture, that many properties are changed. One thing is that the energy is proportional to 1 by Lz square. Energy becomes proportional to 1 by Lz square. Lz means, yes, basically one dimension it is the say thickness. Say thickness. If you sandwich one material, say this is one material, say it is aluminum, gallium, arsenide. Then you sandwich gallium arsenide between two aluminum gallium arsenide. This structure you have sandwiched one gallium arsenide, this is the gallium arsenide layer between two aluminum gallium arsenide layers. So, if this gallium arsenide layer is very thin, say of the order of say 50 angstrom, 60 angstrom, 100 angstrom, that means 10 nanometer, 12 nanometer, then what will happen? The energy will be proportional to 1 by Lz square if Lz is the thickness of the gallium arsenide layer. So, it acts as a quantum well. It acts as a quantum well. Quantum well means there is a boundary, in between there is a well. Okay. And if you can solve the Schrodinger wave equation, all the physics students we have already solved this thing, and you have calculated this thing also. For infinite quantum well it becomes E proportional to 1 by Lz square, right. And this, so what we find that just by changing the value of the thickness Lz, just by changing the value of the thickness Lz, you can change the energy, you can change the energy, right. Till now what we know? We know that the band gap of gallium arsenide is 1.43 electron volt. So, the energy associated with gallium arsenide is 1.43, that is a constant thing. But now you can change the energy of the gallium arsenide by changing the value of Lz. What will happen? You see that this is 1.43, the band gap of gallium arsenide, and the conduction band will split into a number of levels 1, 2, 3, etc. It will split into a number of levels. Why there will be a splitting? The splitting will be due to quantum mechanical phenomena, because of your confinement of carriers, because you have restricted the motion of the carriers, there will be splitting of the energy level. This is E1C, C means conduction band, E1, then E2C, E3C, etc. Similarly, the valence band will also split. This valence band will be E LH1, LH means light hole. How many bands are there in the valence band? In the valence band, when we talk about the valence band, basically there are 3 bands. One is light hole band, another is heavy hole band, and third one is split off band. One is heavy hole, another is light hole, and third one is split off. Heavy hole band, light hole band, and split off band. Okay. Generally 3 bands are there. That means your structure will be like this. There will be 3 bands, one is heavy hole, another is light hole, third one is split off. So, this valence band will also get splitted, and the splitting of the valence band will be E LH1, that means light hole 1, say then E heavy hole 1 HH1 and so on. We do not know actually how it will split, but there will be the splitting of the bands both in the valence and the conduction bands. Now, what will happen? The implication of this is that you see first case in gallium arsenide only transition in 1.43 is available, 1.43. That means, if an electron moves from the valence band to conduction band, then how much energy is required? 1.43 electron volt, and then if it again comes back to the original position in the valence band, there will be electron and hole recombination, and you will get the energy to be emitted in the electromagnetic wave as the electromagnetic wave, right. What will be the measurement of that energy? 1.43, it cannot be more than 1.43. In this case, it will be more than 1.43. How? Because you see that the transition can be from this level to that level, or from this level to that level, or from this level to that level. There are many transitions possible. So, if we assume that the transition is from this level to that level, that means energy will be band gap Eg plus E1c, that means this portion, plus E LH1, that means this portion. So, the final energy becomes greater than Eg. Okay. Now, you can tune the band gap by changing E1c and ELH1. How? Because you can change the splitting depends on the value of Lz. The splitting depends on the value of Lz. You can write a program, you can solve iteratively, then you can plot energy versus thickness, then you choose a particular thickness to get one particular energy. But the material is same, remember, the material is gallium arsenide, and it is applicable for any material. It is applicable for any material. Okay. So, that is the implication of the nanostructure. What happens? First you confine the carriers to a particular dimension, then what will happen? Its energy band will split, and you can expect more energy involved in the structure greater than its band gap, and you can tune those energies E1c or ELH etc. This depends only on the value of the thickness of the material, right. If you have any question, you can tell. This is the quantum confinement phenomena or effect, and it gives you the energy which you can tune. You can tune the energy, you can tune the energy to your possible application. Which one? This energy involved. Now, suppose now there is a recombination of electrons from this structure, then you can expect that the emission wavelength will be Eg plus E1c plus ELH1, right. Earlier only Eg was there. In bulk material only Eg is there, you cannot change the value of Eg, because that is the intrinsic property of the material. But in this case you can tune the energy for a particular application. Okay, so we find that in silicon also there are emerging materials which are based on silicon. Those may be silicon nanostructures. The silicon nanostructure involves silicon nanocrystals, silicon quantum wires and dots, porous silicon. These are the three nanostructures related materials, and in all the cases silicon is involved, you see, because silicon has certain advantages that we have discussed earlier. So, because of these things, that using silicon people have been trying to obtain different kinds of properties which are not there for in bulk silicon, like its application in optoelectronic materials. That is not possible in bulk silicon or crystalline silicon. That is why people have been trying for silicon nanocrystals or silicon quantum wires and dots or porous silicon. And another important, that is not a nanostructure, but it is a bulk material, it is silicon germanium. You see that silicon X germanium 1 minus X. So, you can make silicon germanium, and first I can discuss this material silicon germanium a little bit, because if you see that the carrier mobility of silicon, if you see that the carrier mobility of silicon, it is 1600, but for germanium it is 3900. So, using silicon germanium you can increase the mobility a little bit, okay, because the mobility will vary from 1600 to 3900. So, you can tune the mobility, one part. Another thing is that the band gap of silicon is 1.12 and the band gap of germanium is 0.67. So, you can tune the band gap also from 0.67 to 1.12. Some variation you can make, which otherwise is not possible using silicon. In silicon it is a fixed band gap 1.12 electron volt, but here you can tune the band gap. And for this silicon germanium material I have one thing to add, that you know that in compound semiconductors, and we shall discuss in the next class, that gallium arsenide or indium phosphide, the processing technology is not very matured like silicon. Annealing, oxidation, implantation, diffusion, lithography, these are very standard technique for silicon only. Okay, you cannot use those processing technology, or large wafer cannot be handled for compound semiconductors like silicon, where you can handle very large wafer. So, those are the advantages of silicon, and how you can grow, how you can fabricate gallium arsenide on silicon, because normally gallium arsenide is made on gallium arsenide. Suppose this is gallium arsenide wafer. So, you have to use a gallium arsenide wafer for the fabrication of gallium arsenide layers or p-n junction or MOS device, whatever be the device you would like to do on gallium arsenide. Why? Because of the lattice matching problem. We shall discuss those things also, because of the lattice matching problem. A wafer has a lattice constant, a substrate has a lattice constant, and on which the layer or the crystals will be grown. The crystal has a lattice constant. So, those two lattice constant must be similar in nature, must be equal in ideal case, otherwise what will happen? There will lattice mismatch. Then what will happen? At the interface between the substrate and the layer, there will be defects and dislocation, there will be imperfections. So, when the electron will move from the layer to the substrate or from the substrate to the layer, they will be scattered or trapped inside the interface layers. So, that means your mobility will further reduce, your mobility will further reduce. or for optoelectronic device those will act as a trap center, they will act as a killer center. The recombination will be from those trap and the electron. So, no light will be emitted, the energy will be dissipated as a heat, right. So, that is important thing, that this silicon germanium you can use to grow gallium arsenide. Why? The lattice constant of germanium and lattice constant of gallium arsenide is same. If I give you the value of the lattice constant, you will find that lattice constant of silicon, it is 5.43095 angstrom. Lattice constants of germanium, it is 5.64613 angstrom. Lattice constant of gallium arsenide 5.6533 angstrom. So, what you find, that the lattice constant of germanium and gallium arsenide is almost same, almost same. So, that means mismatch is less in case of germanium on gallium arsenide or gallium arsenide on germanium. But if you think of silicon and germanium, the mismatch is comparatively high. How the mismatch is calculated? The mismatch is calculated by this formula, that lattice constant A of the epitaxial layer or the layer LAYER, this is LAYER, minus A of substrate by A of layer. Using this formula, you can calculate the lattice mismatch into 100%, into 100%. Okay. So, if you take the value of say germanium and silicon, so you can find that it is almost 4%. If you use these two value germanium and silicon, suppose you would like to grow germanium layer on silicon substrate. So, it is 5.64 minus 5.43 by 5.64. So, it will be almost 4%. But you can reduce if you introduce some amount of germanium in it. Okay. That means, silicon germanium compound will reduce some of the lattice mismatch, and I can give you a value that for say silicon of 0.8 and germanium 0.2, the mismatch will be less than 1%. Okay. That means, just by introducing some amount of germanium, the material is silicon, almost silicon, only 2% is germanium, sorry 20% is germanium, 80% is silicon, 20% is germanium. So, if you introduce 20% germanium on silicon, then the mismatch becomes 1% from 4%. So, that is the implication of silicon germanium, that you can and use this silicon germanium for some applications in, and the most major application of silicon germanium is in the detectors, optoelectronic detectors in the infrared region, which is required for defense application, right. In the defense application, you need some very good detector in the infrared region. So, then in that case silicon germanium is used. No, that is a theoretical substance, and lattice mismatch must be 0%. Ideally, the lattice mismatch will be 0%. Okay. But there are other techniques that we shall discuss during our epitaxial crystal growth, those issues we shall discuss. And other materials which are based on nanostructures, you see that these nanocrystals, quantum wires and dots and porous silicon. Now, what is quantum wires and quantum dots? What is quantum wire and what is quantum dot? What is quantum wire and what is quantum dot? If your motion is restricted to say in the xy plane, then that is known as quantum well. If your movement is restricted to say only in the z direction, quantum wire. Okay? It is a where only in one dimension there is a growth, and in other two dimensions the electrons cannot move. The motion of electrons is very restricted in one dimension only. It cannot move in other two directions. Say in this I have given you the example that if suddenly the walls come closer and squeeze me, so I can jump, I can go up and down up to the ceiling. If ceiling and floor is the limit, then I can jump, but I cannot move to the x and y sides. So, in that case that structure is known as the quantum wire. And in quantum dot, yes, the motion is restricted in all the directions. You cannot move. Your motion is restricted in all the three dimensions, and that is quantum dot. And in quantum dot the advantage is that depending on the dot size, the energy is splitted. That I have given you the splitting of the energy levels here. Okay. In this diagram I have shown you that the splitting, it is quantum well basically I have drawn, but in quantum dot also the splitting will be there, and it will depend on inversely proportional to the square of the diameter. Here it is inversely proportional to the square of the width, there it is inversely proportional to the square of the diameter. So, if you can grow smaller and smaller, the energy will be higher and higher. The energy will be higher and higher. So, that is the nano dot or quantum dot, or in nanomaterial, spherical nanomaterial. We talk about spherical nanomaterial. Spherical nanomaterial is basically quantum dot, and the splitting of the energy levels are there, and it depends on the diameter of the dot. Okay. Another important aspect is the porous silicon. Another important aspect is the porous silicon, and there is a technique using which you can fabricate porous silicon. You take a silicon wafer and you metallize on one side. Say this is a silicon wafer and you metallize, say this side is fully metallized, this side is fully metallized. Metallized means you can use aluminum. Okay. Then you take a Teflon beaker. You know what is Teflon? Teflon is a polymeric material. You use it, you take a Teflon beaker and you pour some amount of HF, that means hydrofluoric acid, and ethanol C2H5OH. HF, you take a beaker, you take HF and C2H5OH, say it is 20% or 40% HF, and the rest is C2H5OH. Then you put this silicon wafer inside the Teflon beaker. Now, why we have used Teflon? Because HF is very corrosive. HF is very corrosive in nature. So, normal glass or other type of material, it can destroy. So, that is the reason that Teflon beaker is used, and you put the silicon wafer and you take another electrode, say platinum electrode, and you send a current from, this is an anode, say the silicon acts as an anode and platinum cathode. Between these two, anode and cathode, you send current, say some 20 milliampere, 30 milliampere, 40 milliampere, and the electrolyte is HF and C2H5OH. Under such a circumstance, you will find that the silicon surface is being etched. That means, some of the silicon is getting removed from the surface, and in that case you will get some pores on the silicon wafer, some pores in the silicon wafer. So, the network is silicon, on the silicon there are pores, say this is pores, say the background is silicon and these are the pores, and the pores dimension is millimeter, sorry, in micron or nano. Normally it is micron, but just by changing the current and this electrolyte composition, you can change the dimension of the pores also. The dimension of the pores is very much dependent on the current and the electrolyte. So, you can take 20% HF, then you can take 40% HF, you can take 60% HF, depending on that the pore size also changes, the porosity differs, and you will get a porous structure. I can show you, I do not know whether this structure will be, you can see, no, yes, these are the pores of a porous silicon. You see that this is a pore, okay, this is a pore, and yes, you see that this is pores. Have you seen that there are large magnification here? Yes, you can see that this is a pore, this is another pore, and between two pores there is this boundary. Okay, this is between these two pores there is this boundary, right. This is 30,000 magnification SEM picture, and yes, these are the pores. These are the pores. These are the pores. Basically, there are the air holes. On the silicon matrix, there are air holes. So, what happens basically in this case, in porous silicon, the carrier confinement occurs. That means, quantum mechanical phenomena is achieved using porous silicon because of the dimension of the pores, and this porous silicon is used in optoelectronic application. In visible region, porous silicon can be used. So, normal silicon is not used, but in porous silicon you can use this porous silicon for optoelectronic application, right. So, these are the materials, say silicon normally not used, but some using some techniques you can change silicon into emerging materials like silicon nanocrystal, silicon nanowires, silicon quantum dot, then silicon porous silicon, silicon germanium. Now, why we are devoting so much time with silicon? Because it is the material for electronic industry. Till now there is no substitution for silicon. Now, people have been trying frantically the application of silicon in optoelectronic device, so that it can be integrated in the IC technology. Now, in IC technology there is no scope for integration of the optical side. So, they have been trying for quite a long time, right. Another important material for this elemental semiconductor is diamond. Diamond is basically carbon, it is the allotropic modification of carbon, and this band gap is very high. For diamond it is 5.5 electron volt, wide band gap, but problem is that the processing technology is not available. You can make diamond film, diamond is very hard. So, it can be used as protective coating in many materials, particularly for harsh environment. It is used as protective coating because it is very transparent. You know that diamond is very transparent for a wide range of wavelength, and at the same time it is very hard. So, in harsh environment protective coating is made using diamond, but problem is that we do not have any processing technology using which you can make diamond device. Diamond device you cannot make. Why? Because p-n junction is required. p-n junction is required. almost all wide bandgap material, doping is very difficult to make. Doping is very difficult to make. 5.5 eV is very wide bandgap. So, for this wide bandgap material, you can see that the doping is very much difficult to make, and for basically N type doping is not possible for diamond. P type is available, but N type is not available. So, that is one hindrance for diamond for its application in electronic device, but it has other kind of device application like say protective coating, transparency, etc. you can use. So, now if you have any question, you can tell me. So, till now what we have discussed, basically we have discussed silicon, some nanostructures of silicon, some new materials using silicon, and some introduction about the diamond. So, these are the elemental semiconductors which are used in electronic device industry, and in our next class, immediately after this class, we shall concentrate our discussion on the compound semiconductors.